Brian is a principal software engineer and architect at Red Canary with 2 decades of experience designing everything from signal processing algorithms to scalable cloud-native solutions. He is very passionate about breaking the databases. Today he'll share Go Jump in a Lake, how a data lake can help your security program and why security teams should embrace it. With that, let's give a big round of applause for Brian.
Thank you. I'm gonna talk about databases a little bit here, but we'll get to that. All right, so I'm Brian Davis. Thank you for the introduction. I'm a member of the Red Canary architecture team, and I've been really building complicated systems for a very, very long time. Not related to this talk, but I'm an avid hiker, photographer, home automator, and beekeeper, and I'm based in Denver, Colorado. So if you have any questions about any of that, hit me up afterwards. All right, so not knowing what background you're coming from, not knowing what you're familiar with, I'm going to go over SIEMs, because this is a security conference. Most people use SIEMs, SIEMs, whatever you want to call it, and how we use them and why they tend to get really, really expensive, because all that's going to dovetail into what the heck is a data lake, because I'm here to talk about data lakes today. And then I'm going to talk a little bit how to build a data lake, and then lastly, how a data lake fits into your security program. So let's start with the SIEM use case that we all know and love, which is that you have the SIEM here. Oh, and I forgot to mention, this chart doesn't have any images made by AI. I specifically made a point to not have any artificial intelligence. This is all real intelligence or something that's gone into this. So just, appreciate that for what it's worth. So you have your SIEM and you are trying to aggregate all this data from your environment, right? So you've got maybe some database logs you're putting in there. You've got some web proxy logs. You got a whole bunch of other logs that you're trying to send into your SIEM environment. And at some point, then you start saying, oh, you know what? Well, let's put our EDR telemetry in there too, because that's really cool. Maybe we can find something. Hey, let's put our cloud logs in there. And before you know it, your SIEM starts to expand beyond your SIEM budget. And I thought that this image was the perfect anthropomorphization of what happens to your SIEM when you try to throw all this stuff in there. And it's not here, I'm not here to slam SIEMs. I'm not here to say, this is what's wrong. I'm here to say, this is just the reality of how this works. Right, when you throw all this into something that's not designed to handle this much scale, it's going to become really expensive really, really fast. So, but why? Let's talk about why it is that the technology is like this and what the limitations are. So I'm going to talk about SIEM architecture, but not really, because I don't work for a SIEM company. I don't have insight into SIEM. So I'm going to talk about OpenSearch, because that's an open thing that we can all talk about and understand. So if you have an OpenSearch cluster, you have some sort of master node or some control plane that exists out there, and then you have these big honkin' data nodes that exist out there. These are really powerful computers with really, really big disks that are attached to them. And so I'm going to use an example from actually my company where we have 105 terabytes in one of these OpenSearch clusters, and the amount of scale that's required in order to have that much data inside of there. So whenever you have something like this, we have this really expensive compute that's sitting out there doing a whole bunch of cool and groovy SIEM-like things. And then we have these disks that are relatively cheap compared to the computers that they're attached to. And there's one basic tenet of IT, or really cloud computing. It's that renting computers is expensive, right? This is the cloud village. We all know renting a computers is expensive. How expensive? So this is one of our OpenSearch clusters. It costs us almost $25,000 a month to have this thing out there. And you look at that and say, well, that's really expensive. Why? Well, most of that money is on the compute side. It's that green bar. If you're not colorblind, it's green if you are colorblind. Or in the yellow is the block storage that's attached to it. So if we were to use S3 instead, that would cost us about $2,500. Right? That's like an order of magnitude less in terms of compute, or in terms of storage. And then if you were to put it like into deep archive, cold storage, it's like $100 a month. It's super, super cheap. Why? Well, because there's 432 cores and 3 terabytes of RAM that are sitting out there doing this work to have this OpenSearch cluster out there. And if you're going to start funneling all this data into your SIEM, you have to scale up to that some magnitude of compute as well in order to accommodate that volume of data. So there's a lot of fancy technology and fancy things that this SIEM tool is doing for you. So it's not necessarily a bad thing to have that many cores, but the question you should probably ask is, do you really need that all the time, and what's the ramification of it? So now I'm like 10 minutes into my talk and I haven't actually talked about what a data lake is. And that's what I'm going to start to get into and try to explain how to back into that. So you can go with the cloud provider's definitions, and these are great because there are so many words that actually tell you nothing. A data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. Cool. I don't know what that actually means. And then Microsoft and Google's is a tremendous exact same idea. So that doesn't help me at all. So let's dig into this a little bit more. The way I like to think of it is like the IKEA guy that's putting together little pieces of furniture saying, hey, you're adding storage, you're adding a query engine, and you're adding a data catalog. You're putting those together and forming basically a data lake out of existing technologies that have been around since we came up with Hadoop, right? These technologies are 10, 15 years old. Or if you prefer, it's like 3 raccoons in a trench coat all pretending to be a data lake or a database. And I'll get to that example here in a minute. So let's go back to that OpenSearch cluster that we were talking about. In fact, that the really expensive part of this OpenSearch cluster were those servers, right? So that compute is really, really expensive, and the storage is relatively cheap comparatively, right? So if we can get rid of that expensive compute, we can save a lot of money in this. So let's go delete the computers. Yay, okay, cool. What does that actually mean? Well, now I have a bunch of disks out there. Okay, well, if I have those disks out there, then maybe I don't actually need block storage anymore. I can move them to object storage because I don't have computers that are reading and writing blocks. I just have objects that I can store. So suddenly I can move over into this magical object store category of S3, and that gets me down to like $2,000 a month. Cool. Great, I've waved my hands and suddenly saved a lot of money, but I'll explain how that hand waving can actually happen. So let's go back to those computers and talk about a completely hypothetical use case for those computers, and the fact that let's just say that 90% of the time those computers are sitting there doing nothing for you, right? It's just sitting there idle. And then some of that time you're ingesting data, some of that time you're querying data. But overall, it's not doing anything for you. So let's not pay for those computers when they're not doing anything. Where does that leave us? Serverless computing. The other buzzword of cloud that everyone seems to love, right? Let's spin up the computers when we need them and spin them back down and really take advantage. I just had to use this meme because it's all serverless underneath it, but the magic is there, and I'm doing even more hand waving. So now you have that OpenSearch cluster, and you're spinning up computers when you need to in order to read those disks. And the cool thing about serverless is that when you need to, you can spin up even more computers. And this is handled all by the hyperscalers. They're handling all this stuff behind the scenes. But cool, now I can read the data, and I can write the data, and I can get to what I need to very, very easily. And I don't have to pay for that idle time on my computer. So this allows me to do a lot of magical things, because now I can sprinkle and compute. But there's more magic that's going on behind the covers, right? Because before we were talking about an OpenSearch cluster, and now I've stripped away the computers, now I'm going serverless. But that storage, what's going on with the storage? There has to be some optimization that happens there too. So let's dig into that a little bit more. So when we talk about data going into a SIEM, it's usually JSON data. It's usually log data that we have coming off of our devices. But it's easier to think of this in terms of rows and columns of a table, because it's easier to think of things in terms of databases. So if you've got a database or a row and column set table that has 3 columns and several rows in it, we normally think of storing this in a row-based format, right? This is the way you look at a CSV, A1, B1, C1. This is the way you typically write your data out. And a lot of databases store their data in this particular way. There's another way to store your data, and that's a columnar format. This is really common in a lot of analytical databases like Redshift, and there's a bazillion other ones that exist out there. But in this particular context, by writing the columns out instead of the rows, you can get some interesting economies of scale that you wouldn't get otherwise. So if you encode the data by those columns, you can do some really neat things, and you can enable querying this data in a way that you couldn't before. So let me give you a real example. So this is a table that was dumped out of one of our databases that actually just lists Kubernetes deployments, right? This was on April 1st. I didn't do anything magical to this data. You can see there's a lot of repetition that's going to play in here. So normally, if we were to dump this data out in terms of rows, you'd say, okay, cool. Those are what my rows look like. I understand. It looks like that if I was to do it in a CSV. Our brains comprehend this because we all live in this space one way or another. But if you want to look at it a different way and think in terms of columnar data, and let's just do those first 3 rows again because it's a little bit easier to grasp that, then you can write out a format called Parquet. And for those old enough, they'll recognize it's the margarine spread on the right, that every time I hear the word Parquet, I think of that. Go Google it. It's a terrible commercial from the 90s and the 80s. But anyway, it's not spelled that way. It doesn't really matter. That's a total non sequitur. So if you look at the Parquet version of this, which is a columnar data format, you can see that that same date is repeated 3 times. Then I have some unique numbers that are one-up counters. Then I have the number 1 6 times. I have 1,000, I have 2,000. Oh, okay, there's already some efficiencies that I can see by writing it that way. Plus, if I were to go and search for this data, and I'm searching across a vast amount, it's a lot easier for me to go through one particular column and say, hey, give me everything that has a 1,000 in it, right? And that starts to model the use case of how a data lake is used a little bit more. And if I were to compress that, I could say, well, you know what, it's April 1st, and that's repeated 3 times. Then there's some unique IDs. Then there's the number 1, and it's there 6 times. Then it's 1,000 3 times, 2,000, you get the idea. The thing is, that compression you get for free because the numbers are already written that way. You don't have to gzip an entire file and then un-gzip thing, which gives you some more efficiencies when you're searching it. So if I took this entire file and dumped it out, it was 5 million rows. It was a 290 meg file of CSV. Then I gzipped it, and it was 24 meg. Cool. Okay, that totally makes sense. The Parquet file format was 8 meg. Then I could gzip the Parquet even more and get it down to like 6. But the Parquet file format, which has some inherent compression built in, was already much, much smaller than the other formats that we're used to. And Parquet has a lot of significant advantages, like I mentioned about querying things. And I'm going to grab my water real quick. In terms of how we query things, that allows you ways to search across vast data sets. So let's talk a little bit more about that. So let's say I'm writing these Parquet files out. Right, so I've got a Parquet file with all my data in it. Then I got to go write another Parquet file with more data in it because I'm adding to this data all the time. So suddenly I have 4 Parquet files that I've written out into my S3 object store. And now I've got a problem because I don't know where any of my data is. I don't know which Parquet file has things, and it starts to get kind of messy. Well, so now you need to store some metadata about the data itself so that you know how to go and find it. So then you introduce this manifest file. It lists all the other Parquet files that you're dealing with so you can keep track of it. But you can see already, shoot, now I have 2 manifest files. How do I keep track of those? You can see that this just kind of keeps going. It's like the Russian nesting dolls. So now I need a list of my manifest files so that I know where to go find my Parquet files so that when I write new Parquet files, I've got my tracking there. And if you look at any database system, they all have this really convoluted, complicated system of tracking where all the data is. We just don't ever see it, and we don't ever want to. And then at the very top here, you've got this metadata file that's describing the information about this specific table in such a way that you can make sense of it. And so what do all these things together form? Well, my coworker said it formed a boring Voltron, and so I had to include that, even though it really doesn't look like a Voltron at all, but it looks where he has like hockey guards on. No, it creates something called an iceberg table. And so here's where more magic comes in. So what I just described is a format called Apache Iceberg. So Apache Iceberg is one of many competing data lake formats that exist out there. There's also Delta Lake, there's Apache Hudi, and there's probably a couple others that are out there. But right now, the Iceberg seems like it's winning. Who knows? Could be the VHS Betamax debate of this century. I don't know. But Apache Iceberg allows you to have schema evolution, allows you to have partitioning of your tables, time travel, which means you can go back to any specific point in time in your particular table. And here's the really cool thing, ACID compliance, which means that when you're writing to the table, you can read from it and you still see the same version that you had when you were reading from it. The transactionality is persisted, at least to an extent. I wouldn't use this as your main production database, but it actually gives you some degree of acidity. So all of this combined together actually presents to you a table. Right, those are actually a whole bunch of different files that I talked about, and they're written out to like an S3 file system such that they're just objects sitting out there. But when you use these tools that know how to speak Iceberg, they are presented as a table to you, just like as it was in a database. So this is where those magic comes together in terms of these are just those different piece parts that come together to present to you something that looks like a database, but it's really 3 raccoons in a trench coat. So let's go back to that hierarchy of an iceberg table. And you can see that, okay, we're just going to call that an iceberg table, and it's sitting in an S3 bucket. Now, I could have several iceberg tables, and they can be sitting in several S3 buckets, but now you see the next problem. I don't know where those iceberg tables are, which is really a whole bunch of files, and I don't know which S3 buckets. So now I have to introduce a table catalog. Once again, we're adding more abstraction layers of here's how I keep track of all the things that I live in my environment. So I introduce this table catalog out there. And these are things that all the cloud providers have available to you that are pretty much turnkey, right? So AWS has Glue Data Catalog, Glue Data Catalog, Azure has Data Catalog, Google has the Cloud Data Catalog or BigQuery, or you can kind of go back to the native, which is Apache Hive, which most of these are based off of, and all of this is based off of Spark and Hadoop and the technologies that have existed for a very, very long time. So cool, now I've got a table catalog, so I know where all my tables live, but I have no way to query them. Well, so now you have to layer in a query engine. If you want to go and get this data, you have to have something that knows how to speak Apache Iceberg. So again, the cloud providers have all of these ready turnkey out of the box. AWS Athena is one that you might have used before, or Synapse, or BigQuery. There's also Presto, Trino, and Apache Spark. And I'm pretty sure, and I always get this backwards, Athena is based on Presto, or maybe it was based on Trino. They split at some point. I can't keep them straight. Anyway, it's all the same technologies that know how to speak Iceberg, that know how to read the table catalog, that know how to get the data. So then when I want to go query that data out of my lake, I go and hit the table catalog. I say, oh, cool. Where do my tables live? Oh, okay, now I know where they are. I can go and read those Iceberg things, which is really a set of files, and I know how to go and get the data that I want. And so you might look at that picture and say, this is terrible. Why the hell would we ever want this? And that's a reasonable response until you look at an architecture diagram for a normal database. I shouldn't say normal because they're all weird. Like here's Postgres and MySQL. I don't understand them either. They're just as complicated on the insides. You just don't ever crack them open to actually look on the inside. They just work that way, right? And so we've effectively done the same thing here. We've built a database from first principles, and we've stripped out the computers and we've stripped out the storage. So where does that leave us? I honestly don't remember. Oh, right. You can store a lot of data. Right? So here's where the power really starts to come in by stripping out those bottlenecks we talked about. They're just written to S3, right? And I don't know about you guys, I've written a crap ton of data to S3 before, and it just works. Same thing is true with Azure Blob Store, and I haven't used GCP very much, but I trust that it just works too. The technology is incredibly scalable. And then you can query a lot of data because you have a lot of data that you've written out there. Those queries are federated across thousands of files inside of your object store, and you can scale it. I know, and in my bio, I talk about how much I hate databases, and that's a true story. We're always limited by that one database server or the cluster of database servers, and you can only push them so hard before they're like, no, I don't want to do this anymore, please let me go home. Well, now we're talking it's serverless. We can spin up as many shards of these things as we need to, and this is all happening behind the scenes, such that you can query that federated data store in S3 as much as you want to, and you really don't suffer those same limitations that you do when you have a single database server. So all of that is really pretty cool in terms of that's what a data lake enables you to be able to do, is basically build this really honking big database that is serverless, that lives in the cloud, that is relatively cheap. So when I say heaps of data, I didn't say heaps of data, but I said heaps of data now. So how much can you really store out there? Honestly, we haven't stored this much in our data lake yet at Red Canary, but I was in a presentation this last December at Netflix, and they're the ones that came up with Apache Iceberg, so of course they're the ones that have the coolest stats. They had an exabyte of data in their data lake, which that's a lot of data. 3 million Iceberg tables. Their largest table is 36 petabytes. They ingest 10 petabytes per day. They're deleting 9 petabytes per day. And there's just a lot of activity going on in that data lake. So this tells me this technology can scale. Now, obviously not everyone's Netflix, so your scaling mileage may vary. However, that's pretty darn cool in terms of what's capable of doing. And I know that I've used S3 a lot. I've used these other cloud technologies a lot. They do scale really well. So what's the catch? Like anything else, I'll let you go back so you can snap a photo of that because it's a really cool slide, particularly the Jaws reference. So what's the catch? Well, like anything serverless, you pay in a very unexpected way, right? If you're going to go and query a lot of data and you scan a lot of data, you're spinning up a lot of computers behind the scene, especially if you're using a cloud managed service like Athena. Behind the scenes, it's spinning up all those serverless computers to go and do all that cool work for you. And you can end up paying a lot on the back end. And it's incredibly difficult to predict how much you're going to pay because it depends on the query that you're running and the way that your data is partitioned and the way that you're spinning up your particular query engines. So it's complicated. However, you could still be saving a lot more than if you tried to pump it all into your SIEM to begin with. And so a lot of it has to do with the shape of the data that you're storing. And so it's one of those things that's really difficult to tune until after you've paid your very large cloud bill. So let's talk about how you would actually go and build a data lake, and let's see if I actually got that song stuck in your head. If you have kids, I did. If not, then you have no idea what that reference was. So there's like 4 key phases inside of a data lake. Now let's talk through them. Most of the time when you read about ingest, if you go and search data lakes on Google, you get all this stuff about you get extract, transform, and load, ETL transforms. That's the way that most people use data lakes. They're pulling data out of a database and another database, and they're transforming it for some back office analytic work. Well, that's not the security use case that we talked about before. In fact, that's a really hard use case to kind of find references for, because what we want are these streaming log sources coming in to S3 and being written in a useful format for us in the future. And so when you're going and looking at how do I go build my own security data lake, it's hard to find references like that. But the good news is there's a lot of technologies out there that exist already that do this. A lot of them are native within the cloud providers, right? Data Firehose, Data Factory Pipelines, Dataflow are some of the ones. Or you just go and use Spark and Flink off the shelf. It's open source. This is what all those technologies are based off of that can stream your logs in a certain way, and they all have native Iceberg format support. And you simply say, go write Iceberg files that are in this particular shape and size in this particular location. So now you have to store them. I talked about this. It's S3, it's blob store. Now most of the cloud providers have specialized blob stores that actually, in theory, do Iceberg tables better. I don't know, they're relatively new. We use AWS primarily, and that's a relatively new feature. I've heard that they work well, but we haven't experienced that yet. So then you want to process that data, right? There's no value in just pumping this into a data store. You actually want to build analytics. You want to go back and query that. You want to look for threats across all those different things going into your data lake. There's a whole host of tools that you can use to do that, right? Whether that's an Athena query that you just go and run, or you run something in Spark or Elastic MapReduce that says every 5 minutes, I want you to go run this query against all my data, just like you would go and build a query inside of Splunk or inside of whatever SIEM tool that you use. And then the last thing is, well, maybe you want to go dumpster diving. Maybe you want to go see if there's patterns in there. Maybe you want to try to find, I want to show me everything, every time we've logged in from this particular IP address over the last period of time. Well, there's a lot of tools to do that too. Once again, we're gluing these together, which is somewhat unfortunate because there's no out-of-the-box solution. Actually, there are, but that's a different story. But if you want to look at one of them is Apache Superset. This is an open source tool. It's really pretty cool. These are some dashboards that my team has built that show you ways that we were querying our data lake for security data. I don't even remember what these were specifically for. I think some of them were logins and suspicious activity that were happening over time. And each of these dashboards took about 5 seconds to load. Not quite as snappy as you would when you're looking around in Splunk. And every time we hit that dashboard, we're paying a little bit of money, but a lot less money than we'd be paying if we had those 432 cores just standing at the ready to ingest all that data. And those dashboards are built with SQL, or something that looks alarmingly like SQL. So if you have a security team that knows how to use SQL or knows how to write queries in whatever query language of choice, then you can pretty much get there with Iceberg as well, because it's a familiar abstraction that a lot of our security teams are already familiar with. So this is a talk about data lakes and security. I'm going to kind of tie these last little bits together and say, well, what is the security use case? I've kind of highlighted them as I talk through here, but the bottom line is, as we continue to pump more and more data into our SIEMs, it's getting harder and harder to do that without our CFOs coming in yelling at us because we're breaking the budget. So there's so much data volume that we have to put it somewhere if we want to store it. And a data lake gives you a really, really good option to do that and do it cost effectively. In a similar vein, it might be that your SIEM setup is only like a 3-month long retention period or whatever you can afford to do. Well, if you want to store data for longer, Putting it in a data lake gives you more of that optionality, because now you can hold on to that data for a much longer period of time, and you can look for trends, you can look for things over the course of a year or several years. Or maybe there is some incident of a breach that happened that started months or even years ago. The example that I keep coming back to is when the SolarWinds thing happened a couple of years ago. People were looking back in their logs several months in the past to say, did I see an active infiltration that happened? And most people's log retention didn't go back that far. Or there's also the write once, read never use case, which says, you know what, for compliance reasons, I have to save this. I don't want to save this, but I need to put it somewhere. I don't want to put it somewhere expensive, so I'm just going to write it. And every so often I go and query it to say, yep, I can pull it out when I need to. Cool, it's there. And then there's a bonus use case, because we're at a conference where everyone's saying AI in every single presentation. Data lakes and AI go together like, peanut butter and jelly. I don't even know what the right metaphor there is. A lot of data is really powerful for machine learning or AI training or anything else along those lines. It allows you to do a lot of really cool things that you couldn't do if you didn't have this massive corpus of data. If you're aging your data out after 3 months, you don't have that big history. If you've got data going back for years, that's really beneficial. So the main point I wanted to drive home here is that a data lake is a great tool to supplement your security toolbox. And I want to foot stomp a point here that one of my coworkers gave me some feedback. This isn't going to replace your SIEM. There's really no way that it can replace your SIEM, because your SIEM is taking in so much data in real time. But at the current state, it's a really good way to augment your SIEM tooling that you have. And a lot of SIEMs offer this as an extension. You can basically say, yep, my SIEM now has some sort of offline storage or data lake capability, which is great. And that's one of the reasons why that these are becoming more and more prevalent. The thing is, it acts like a SIEM, allowing you that correlation and analysis. It gives you the ability to do things across a larger data source in a way that you necessarily couldn't have done before with a tool like a SIEM. So on that note, I'll open it up if there's any questions that people have about data lakes, about beekeeping, about anything.
I have a question.
Yes.
Mostly the question is on the search aspect. So on SIEM side, right, you don't pay for searches. So here, if the table, I don't know whether the indexing happens in this or not.
So the question was paying for searching. You don't pay for a search on a SIEM.
Yeah.
But then the question was, is there indexing on a data lake, and how does the search cost?
Because it's undefined in the sense how the cost is going to fare.
Yep.
So what would you suggest? Like if someone is trying to design this kind of structure, so what is going to work and what may not work? Like you can write complex queries. I don't know. If there is no index, it will go and try to fetch everything.
So you're absolutely right. If there's no index, it's going to go and try to fetch everything. Parquet out of the box is at least better, I think, at building. It's probably not called an inherent index, but that's just what I'll describe it as, to say, because it's a columnar data format, you don't necessarily need to have an index on every column like you would in Postgres. It's actually pretty darn efficient to query, and we've seen this in all of the use cases that we have, that you are not querying as much as you might think you were querying if you were thinking of it in terms of a typical database. Now you're right, in a SIEM, you're not paying per query because you're paying for those, to use my example, 432 cores that are just sitting there at your disposal at all the time. So you are paying for the query, it's just the query you haven't made yet. So to answer your specific question of how would you tune this to your specific use case, depending on the types of queries that your users are submitting, that might dictate how you're slicing up the data. Apache Iceberg doesn't have any built-in extra indexes that you can add. However, there's another format called Apache Puffin, because we're going with apparently the Antarctic theme, that allows you to add in indexes. Those are really new. I don't know, I haven't used those yet. So I think there is a need that's evolving, and like everything else in this really fast moving technology space, it's probably going to get added over time. But I think the answer is look at the queries that your users are running and decide if you want to tune your data accordingly. Because one of the other things about a data lake that I didn't talk about, is there's something called a medallion architecture that's really common, which is to say, you know what? Because storage is so cheap, make a copy of it. Figure out the queries that you want. Figure out the prevalence tables that you want. As an example, in my company, we have login prevalence indexes that we build. Basically, it's another table that we make on the side so that we can go and query, hey, how often has this user logged in and from what devices? And I don't have to go query my entire table. I query a copy of that table. And that in the medallion architecture, they call it bronze, silver, and gold. Basically, you refine the data to be more of what you're looking for, more of what you're searching for.
One more question.
Yes.
I saw the Apache Glacier. So I read it long back. It takes a time to retrieve data from Glacier. So in that case, how does it work? Let's say Athena is the layer which tries to query. So we need to add that time up in the query, or?
So the question was, how long does it take to access the data that's living in Apache or in AWS Glacier? That's a really good question, and it kind of depends, because now AWS, at least, and I can't speak to Azure or Google, have like 15 different flavors of Glacier, including like 5-second retrieval times, which I don't know how accurate that is, but it's not as expensive as hot storage. It's not as cheap as cold storage. It's like tepid storage. I don't know what they call it, but you can absolutely mix that in. So they have a tiered pricing thing with it, intelligent tiering, that's what it's called, that will move the data around accordingly. Obviously, if you're going to query terminology. You're going to query Glacier data frequently, it shouldn't live in Glacier because that's going to be expensive to thaw that thing out. The Glacier use case is more for that write once, read never use case where you really don't think you're ever going to go and get it. But if you do have it, all you have to do is thaw it out, and if you're on normal Glacier, it's going to take you 12 hours. If you're on the fancier Glacier, it's going to take you a couple of seconds. And in that particular case, I think Athena will wait for it to thaw, and that's no worse than some of our Postgres queries that we've done at my company, so maybe that's normal.
Thank you.
Yeah.
Thank you for sharing, because I see a lot of next-gen SIEM companies trying to follow similar kind of plans.
I mean, I'm up here because we have a data lake too, because it's becoming a more and more common trend. But the reality of it is the technology has matured enough that it's become a viable security option. And as I said this before, it's not going to replace a SIEM. It's not going to replace your other technologies that you may have for monitoring, but it can absolutely augment it, especially when you want to start dumping in a crap ton more data of other flavors, and you don't know where to put that. Awesome. Well, thank you guys for your time. I appreciate it.